Okay, we're going to talk about a whole heap of calcs here. You can see I've got the scenario there. This is about fault loop impedance, but it's also about current carrying capacity. So what we're going to do is, over a series of videos, we're going to do a whole scenario and work out everything. So we're going to look at this scenario. I'm not going to go through the whole thing with you. What I would encourage you to do is just hit the pause button, have a look at what I've laid out there, at all the different, at the cons mains. We've got the cons mains there, sub mains, final sub circuit. So we're looking at one scenario. We're going to work out all the cable sizes based on CCC and voltage drop. We're going to then work out the fault loop impedance, the prospective fault current, and the short circuit temperature rise requirements. That's what SCTR stands for there. So, but we'll start with the cable size, because we can't work out the fault loop impedance without the cable size. So we'll start. I've got the main switchboard here, which is being fed from a transformer. Then I've got the DB, then I've got the motor there, and so we'll connect it all up, just so we can see the circuit and how it all works. So we've our cons mains is coming down there, and our sub main to there, and our final sub circuit active. Now, of course, these sets of cables are all three-phase, as you can see there, and the final sub circuit is single phase. That just throws a little bit of a different loop, which is useful to consider. So obviously we're running in neutral to the main board and to the sub board, and obviously to the final sub circuit. Now we've got to put some earths in. Now, as we've done in previous videos on fault loop impedance, we're just showing the earth here. Of course, there's no earth in the cons mains, and made a point of saying there's no earth in the sub main either. There's an MEN at the distribution board, so there is no earth in the sub main there. So we'll just put in the earth bar here, and the stake. Always, whenever you have an MEN link, you have a stake as well. And then, of course, the final sub-circuit needs an earth, the frame of the motor. All right. So that's going to leave us in good shape to have a look at some of this other stuff. Now, as you can see, as I've got written here for the three-phase sub main, the three-phase cons mains, we've got a circuit breaker is 250 amps, and of course these are the final sub circuits coming off that. The circuit breaker for the DB is 80 amps, so that's actually here, so we can call that 80 amps. I'll write it down here. I'll write it down here so we don't get too congested up here. And of course the final sub-circuit has a 32 amp type C. I didn't mention the type of the others because it's not really relevant. And so we've laid it out there. So the first thing we've got to look at is the current carrying capacity of the cons mains. Now this is going to take a while. It's going to take a while to do all of this, so pause the video whenever you think it's necessary and check what I've done, because I'm going to be throwing out a lot of tables and item numbers and columns and stuff. So if you're not sure, I encourage you to follow it by pausing when you need to, checking it in AS 3008, because that's what we're going to be going off, and so at each point you can follow it with me and make sure you know that you're going to the right table and the right column. Okay, so starts with cons mains. We'll find out the CCC of the cons mains. So we'll start with the cons mains, and of course it's three-phase. We'll start with current carrying capacity, and as always when we start with current carrying capacity, we start at table 3, and in this case, because it is in trefoil on perforated cable tray, that's 3.1. And if we scroll down, we find we're looking for cables in trefoil. So if you go to 3.1 and scroll down, we want single coil cables. So it's on the first page of 3.1. Scroll down and find it's on cable tray, so that's item 5. So this is the line that we look for, that you've started out correctly. So we going to item 5. If you run your finger across, you find table 7 and table 8, and we know that it's table 8 because it's X90, so it's table 8, and we know that it's column 5 because we assume it's stranded. Always assume the cable's stranded copper unless you're told otherwise. And so that's where we come back to. That's where this is table 8, column 5. That's where we're going to come back to at the end to work out what size cable we need. So first thing you need to know is that there's a derating. So if you look here, is there a derating? And of course it says touching 2 other circuits. So whenever a circuit is run with 1 or more circuits, there's going to be a derating because they feed off the heat of each other. So derating, if you're still on table 3.1 there, slide your finger across to the right hand side and you'll find that the derating table for this is table 23. But there's also a rating for ambient temperature, and so it tells you that it's 55 degrees. So we call that rating for AT, and that's going to be table 27. So this is where we go to find out our ratings and deratings. So if you go to table 23, look for the trefoil configuration, and of course it's touching and not spaced, so that's a different item. We're looking at item 4, and we're looking at column 8. If you look at column 8, you'll see it's touching 2 other circuits, so 3 circuits in all, and it's going to be 0.87. That's our first one. And for ambient temperature is always table 27. And so what we've got to find in table 27 is we're looking for the temperature. And you'll see 55 degrees is in column 10. Run your finger down to 90 degree cable and it's 0.81. So there's that. Now, what we've got to find out is, well, we know that the breaker will trip at 250 amps, but what we're really looking for is, well, how much heat is that going to be generating? Well, we know it's going to be excessive heat because we've got it running with a couple of other circuits and we've got it in a place that's already hot. And so we have to up the current rating for that cable. So what we're looking for is, I just call it I heat. So the heat value we're looking for is going to be 250 over these factors. So 0.87 times 0.81, that's 250 over that. Turns out we've got the equivalent heat of 354.8. So that, we need a cable that'll take a lot more than 250 amps because of the way it's been installed. And so we plug that number back into table 8, column 5. So we go back to table 8, column 5, and we'll just quickly have a look at that now. So if we go to table 8, column 5, I'm not going to do this for every table, but if we go to table 8, column 5, there's column 5, we're looking for 354.8 amps, and we see, well, 120 won't do it. It's going to have to be 150, which will take 403 amps. So that, as far as current carrying capacity is concerned, that's the size cable we're going to use, 150 mil. But of course we haven't considered voltage drop yet. Now it tells you for the cons mains we're allowing 1% voltage drop because, well, you've got to spread your 5% over the 3 parts of the circuit. We can only get 5% from across the whole of the entirety of the circuit, starting from the cons mains and finishing at the final sub-circuit. We only get 5%, so we're allowing 1% in the cons main. So voltage drop is 1% of 400, of course, because it's 3-phase. So it's just 4 volts. So then we're going to look for what's the maximum VC we can use. Now VC is the voltage drop in the cable in millivolts per ampere meter. And that, as it turns out, we work out by 4 times 1,000 over length. It says the length there is 51 meters. 51 times 210. The current, we use 210. We don't use the circuit breaker. We use the maximum demand. So let's put that in an equation. 4 times 1,000 over 51 times 210. That equals 0.373. 373 millivolts per ampere meter. All right, so what we do then is we go to a voltage drop table. Now, of course, there are a few voltage drop tables. The one we're interested in is table 40 because that's the one for where it's laid in trefoil. And of course, it's 90-degree cable. So we're at column 10. So we write in our table reference, table 40, column 10, and we scroll down. We scroll down there, table 40, column 10, here we are. We're looking for a maximum of 373. It can't be any bigger than that. So down, oh, we're right on, 373 there. We could get away with 120 mil. But of course, 120 mil, but we're not going to use 120 mil, are we? Because we have to use 150 for current carrying capacity. So, we must use 150 mil squared. So we can write that in here, 150 mil squared. So we must use 150 mil squared. We're stuck with it, which just coincidentally, well, incidentally anyway, has a millivolts per ampere meter rating, 0.316 millivolts per ampere meter. That's what we're going to use. That's the minimum, but because the CCC requirements are greater, we go with that. So let's do the submain now. Okay, three-phase submains. Submains, and of course we always start at table 3 something. Now of course, as you can see here, it's buried in conduit, so it's underground in conduit. That's table 3 4. And of course if we go to table 3 4, have a look there, turns out that we're looking for a 4-core on Earth. So of course they won't mention 4-core because one of the cores is neutral. We're only interested in, it's going to be a 3-core cable we're looking for. So we have, we scroll our finger down, we find it's item 4 is what we're interested in. Item 4, and running our finger across, we find that we get table 13 or 14. Now in this case we pick 13 because this is V90, which means it's a 75-degree cable. If you remember that from your lessons, a V90, it counts as a 75-degree cable. So we pick table 13, and it's going to be column 25. That's where our cable size is coming from. And of course there's no derating here, but there's lots of ratings. There's no derating. That's because there's no other circuit. Alright, but there's a rating, there's a few ratings there. First one, rating for depth. And that's table 28.2. I would encourage you to follow these. Pause the video, just check where I got that from. Don't take my word for it, check me. And we've also got soil ambient temperature. Ambient temperature is table 27, but because we used table 27.1 there, but this is table 27.2. And there's a rating for soil thermal resistivity. I'll just call it STR. And our soil thermal resistivity there is 1 degree C meters per watt. Alright, so that's going to be table 29. So there's a few ratings there we have to contend with. And if we're on table 28.2, you'll find it's column 6 because we are multi-core in conduit, and we're at 0.8 depth. So it turns out that that's a derating of 0.95. And soil ambient temperature from table 27 is also column 6, and that comes to 0.95 as well. And soil thermal resistivity, column 4, it's actually above 1 in this case, 1.02. So there our rating factors, because it turns out a soil thermal resistivity of 1 gives us, uprates our cable a little bit. So we use the same method as we used here. We want to find I heat, and so that's all those things on the denominator, 0.95 times 0.95 times 1.02. Okay, so it's the circuit breaker is 80. Pretty sure, yep, circuit breaker is 80. So if we bang that in the calculator, we'll get something a bit above 80, I'm sure. 86.9 amps. So that goes into our table up here. And we find when we go to table 13, column 25, we'll have a look at that now. Table 13, as you can see, 13, column 25, we're looking for 86.9 amps. And here it is, table 13, column 25. 73 is no good, 94 is what we want. Turns out it's 25 mil. So we're looking for 25 mil cable. That's what that says there. So our submains is in 25 mil at least, because 25 mil is our current carrying capacity requirements. And for voltage drop, we get 1.5% for our submains. So 1.5% of 400 is 6 volts. And so we're looking for the maximum value of VC, 6 times 1,000 over the length, which is 47 meters, and the current is 70. If you're not sure why I'm using 70 instead of 80 for the breaker, it's not illegal to use the 80, but I've asked you to select the minimum size, and to be sure you got the minimum size, you use the smallest amount of current you're allowed to. So go to 3.6.2 in the rules in AS3000. Go there, check it out. Trust me, you're allowed to use 70. And so we bang that in the calculator and we get 1.824 millivolts per ampere meter. Now, of course, this is multi-core, so we probably, some of you probably know off the top of your head, multi-core straight to table 42. And it's 75-degree cable, so you go straight to column 6. All right, and then we run our finger down that, and you'll find that, as it turns out, 25 mil is the right size cable. So we can get away with 25 mil cable. All right, so 25 mil. And it turns out 25 mil is 1.54 millivolts per ampere meter. It's not particularly relevant now once we know the answer, because we're looking for the cable, but it'll be relevant for what we do in one of the later videos. So all right, so finally we got a final sub-circuit here to deal with. We need the size of that, and first thing we want to do is work out okay, so it's single phase, but we're not given a connected load. We're given a circuit breaker size, but we don't know exactly what the current of the motor is going to be. So we're not given a maximum demand or a connected load, but when it comes to voltage drop, we want to use that because that'll guarantee us the smallest size cable we can get away with. So first thing we should do is work out current in the load, just as a thing to get out of the way real quick.